We're solving problem 19 from the 2021 F equals MA. A cavity of radius r over 2 is dug out of a spherical planet with uniform mass density of mass m and radius r. What is the magnitude of the gravitational field at point P in the diagram below? So we want to find this point P, and we have two gravitational fields because we consider this cavity as negative mass in this case. So it goes this way and that way. So for field 1, G1, this is pretty simple. It's just Gm over r squared. Like usual, you know, gravitational fields. But for the second one, it's going to be different. So this is going to be G, but the mass of this, since it's a fourth of, since like the crater is, well, it's like a fourth of the total big one, you're going to be dividing by 8 because that's like how it is in relation to the mass with the big planet. Since the mass is the spherical planet with mass m, and then instead of r squared, it's going to be d squared, or the distance between the center of the cavity and our point P. Well, for distance, if we look at the lines we drew, which all represent something, this is the radius of the cavity, this is the distance, and this is the radius from the center to the edge of the planet, because we know that this is a half, therefore this point must be the center of the whole planet, including the cavity, but that's not really important. So what we see is that, well, if you just draw this line down, point P is going to line up with this point right here, the center of the entire thing, forming a right triangle. We can then use the Pythagorean theorem to denote that d squared, the hypotenuse, is equal to r over 2 squared plus r squared, or 5r squared over 4. So then our second gravitational field, we can substitute in that value of d. This is Gm over 8 over 5r squared over 4. Now these can cross out, and then there's a divide by 2 left, or divide by 2 left over, multiply by 2. Second gravitational field is Gm over 10r squared. Now at this point, the value of theta, well, we can find various trigonometric values to express this angle. So there are two identities that we really want, and you can probably find this because calculators are allowed in this test. Cosine of this angle is 1 over the square root of 5, and the sine of angle theta is 2 over the square root of 5. Well, then the total gravitational field is equal to the sum of the two fields. So G2 plus G1, which is, well, we have the first one, G1 is pretty simple, negative Gm over r squared. So we just write out the expression for basically how we solve for the gravitational fields, I guess. So we can do this by plugging in the values and using those trigonometric identities to help us solve this equation. So this is going to be 5 root 5 r squared. Well, this expression, we then can just take out a Gm over r squared. If this is Gm over r squared, this brings out like two things. First one is negative 1 over 10 root 5. And the other one is 1 over 5 root 5 minus that 1 we got from over there. This is essentially what we want. So if we can just rewrite it over here to not get too messy, our total gravitational field is the square root of the squares of all these values. So this is square root of 1 over 10 root 5. Not writing it, I could write it negative, but writing it negative, it's not really going to do anything if you square it, but it just helps showing it. So you basically square these two things that you get. This is 1 over 5 root 5 minus 1 squared. And and then you multiply by gm over r squared like usual. And then, well, it might seem hard to do this, but you have a calculator. Calculators are allowed. So like basic ones that can help you solve square roots and like decimals, round to 3 points. This is 0.912 gm over r squared. This is our answer when you just put this into a calculator.